Ionization. In this section, we consider the equilibrium of systems that are made of ionized gases. Systems that are made up of ionized gases. Or plasmas. A field that has been studied and apply increasing in the recent years. In the previous sections, we discussed chemical equilibrium with particular emphasis on molecular dissociation. Equilibrium with a particular emphasis on molecular dissociation. As for example, the reaction N2 which occurs to an appreciable extent for most molecules only at high temperature. Occurs to an appreciable extent for most molecules only at high temperature. Have the order of magnitude of Kelvin. At still higher temperatures, such as those found in the electric arcs, the gas becomes ionized. That is, some of the atoms lose an electron according to the reaction. N where N plus denoted a slightly ionized nitrogen atom. Singly ionized nitrogen atom. One that has lost one electron and consequently has a positive charge, and E bar represents the free electron, E minus represents free electron. As the temperature rises still higher, many of ionized atoms lose another electron according to the reaction. For example, for nitrogen, with losing another electron, and thus becomes doubly ionized. As the temperature continues to rise, the process continues until a temperature is reached at which all the electrons have been stripped from the nucleus. Ionization generally is appreciable only at high temperature. However, dissociation and ionization both tend to occur to greater extent at low pressure. Consequently, dissociation and ionization may be appreciable in such environments as the upper atmosphere, even at moderate temperature. You can take note, ionization generally is appreciable only at high temperature. However, dissociation and ionization both tend to occur to greater extent both to occur to greater extents at low pressure. Consequently, dissociation and ionization may be appreciable in such environments. As the upper atmosphere. Even at moderate temperature. Other effects such as radiation will also cause ionization, but these effects are not considerable here. Radiation also cause ionization. but these effects are not considered here. The problem of analyzing the composition in a plasma becomes much more difficult than for an ordinary chemical reaction, for in an electric field that free electrons in the mixture do not exchange energy with the positive ions and neutral atoms at the same rate that they do with the field. Consequently, in a plasma in an electric field, the electron gas is not at exactly the same temperature as the heavy particles. However, for moderate fields, assuming a condition of thermal equilibrium in the plasma is a reasonable approximation, at least for preliminary calculation. Under this condition, we can treat the ionization equilibrium in exactly the same manner as an ordinary chemical equilibrium analysis. At this extremely high temperature, we may assume that the plasma behaves as an ideal gas mixture of neutral atoms, positive ions, and electron gas. Thus, for ionization of some atom species I, we can write this relation for the ionization of some atomic species are A equals to we may write the ionization equilibrium equation in the form ionization equilibrium equation K equals to Ya plus by P of P0 the ionization equilibrium constant K is defined in ordinary manner. We have also ln K that gives change RT and is a function of temperature only. The standard state Gibbs function change for the reaction can write as this relation G A plus G bar 0 E plus the standard Gibbs function for each component at the given plasma temperature can be calculated using the procedure of statistical thermodynamics, so that ionization equilibrium constants can be tabulated as function of temperature. The ionization equilibrium equation is then solved in the same manner as an ordinary chemical reaction equilibrium. Application of the chapter is the next section.